welcome everyone. Next Tuesday, we had a couple of speakers that could not make it. So what we will do is have a roundtable discussion like we had last year, where we sit around the table. It turned out that this is actually much more informative than the standard forum that we have. We get to hear about what people are working on. So we have that the same time, Tuesday next week. It's 2 days before Thanksgiving, but nevertheless, we won't have a turkey though, right?
Unfortunately, yeah.
So at 1 p.m. We will have a table here and sit around it and hear what each of us is doing and so forth. The other thing I wanted to mention, and that's very sad news that I communicated yesterday. Jeff McClintock, that was an affiliate with the Black Hole Initiative, passed away. He was a close collaborator of Ramesh, also worked with Andy and myself. And if we had to characterize him with one word, he was probably the most decent scientist that at least I'm aware of, and I think that word captures a lot of his integrity and truthfulness and readiness to help everyone. So anyone that interacted with him knows how special Jeff was, and we mourn losing him. But this was an outcome of a terminal disease he had over the past year, and many people anticipate. There was a workshop in his honor several months ago where people talked. He was there. But interestingly, even though he knew that it's terminal, he continued to be very excited and interested in science, and that's what he did until the last day. So that also shows his remarkable character. And so let's start with the speakers of today. Go ahead.
Good afternoon, everyone. Our first speaker is Xinliang An. He's a Fields postdoctoral fellow at the University of Toronto, and he's speaking to us about the formation of singularities at GR.
Thanks very much for the organizer's invitation. It's a great pleasure to be here. So I'll talk about singularity formation in general relativity. So the goal of this talk, so within the framework of general relativity, we will see how to use pure gravitational waves, Einstein vacuum equation, to create a black hole region in our spacetime. So today we'll talk about Einstein vacuum equation in Rn plus 1, n larger or equal to 3. So the equation is just a very geometric equation with Ricci curvature equal to 0 for Lorentz manifold. This is a hyperbolic system for metric G mu. So for this equation, we use several explicit static or stationary solutions in R3 plus 1. For example, the Minkowski solution, which is a trivial solution, and the famous Schwarzschild solution with mass, and a slightly more difficult family, which is with both mass and angular momentum curve solution. These solutions are stationary solution or static solution. They are for the black hole solutions. They are there from the black hole region was there from t equal to minus infinity to t equal to plus infinity. So based on Einstein vacuum equation and this very simple fact, so we could ask 4 natural questions. The first, can black hole region actually form dynamically in vacuum? In the initial data, we do not have black hole region, but black hole could form in evolution. So this turned out to be a really hard question, but it was open until 2008. In a 600-page monumental work, Quistolo showed that the answer is yes. And so now, around 10 years later, so now we can give a more systematical way to simplify Quistolo's work. Not only we want to simplify Quistolo's work.
This is completely separate from the Christodoulou and Kleinerman showing that there's a region in which black holes don't form, right?
Right. So this is a large data problem. So for in 1993, Quistolo and Kleinerman proved Sylvie Minkowski, which is for the initial data, if it's small, there's no black hole region at all in the future. But this is a pure large data problem. Quistolo need to prescribe some large data such that a black hole region could form. But Quistolo used the framework of Quistolo-Kleinerman.
Why is it a hard question?
Yeah, because
so we have like these explicit. I mean, if you have a scale of some examples.
So this is Einstein vacuum. So So vacuum, this is hard. So if you have matter, it's easy. You can just throw the matter to the center, you can form a black hole region.
Yeah.
Now it's vacuum. We cannot impose spherical symmetry. If we impose spherical symmetry by Bohm's theorem, we only have Schwarzschild or Minkowski.
Right.
So crystal need to do the system. So this is hard. So yeah.
So there is no energy density in the system that makes the black hole.
Yeah. So the shared
Or gravity wave.
gravitational wave.
Ah, okay.
So there's something new crystal will observe. But I will talk about this later. So okay. So after crystal's work, we not only want to simplify, we want to improve its result to a sharp case. So to form a black hole in Einstein vacuum equation, what is the least size of the initial data? So intuitively, the larger the size of the initial data, the easier to form a black hole. Now we want a sharp result. Together with Jonathan Luke, with at Stanford, we proved a scale-critical black hole formation criteria, which is our initial data is much smaller than crystallose, and we need to go further toward the center. So in crystallose work, he introduced a small parameter delta, and the crystallo form a black hole of radius 1. So now we still with the same parameter delta, we introduce another universal large constant A, like 1,000. We form a black hole of radius delta times A. So in another way, crystallo confine all the singularity in a ball of radius 1. We confine all the singularity in a very tiny ball of radius delta times A like 1,000.
Well,
And
yeah. The Einstein equations have a scale symmetry, so if you have a solution that gives something of radius 1, you can rescale it and get a new solution.
So crystal's result is not scale critical. So this result isn't scale critical.
Sorry, what is that?
Yeah, so I will explain it very soon. Okay, so yeah, our result is the first scale critical result for Einstein vacuum equation with no symmetry assumption. So okay, so yeah, so maybe I first state the theorem and then we'll go back to this issue. Okay, so now we have a sharper result compared with crystallo. We can ask the following another question. So we know that we can form a black hole region. Can we find the boundary of the black hole region? And can we show that all the black hole region actually is dynamically forming from one point? So in a new preprint this year, I'll give a positive answer to both questions. So here I combine techniques from both hyperbolic and elliptic PDEs. And with hyperbolic PDE, I solve and control the system region up to the center. And by solving a new family of quasilinear elliptic PDEs, I find the boundary of the black hole region. It is a dynamical horizon emerging from a point. So the first three results are about the black hole formation, and the fourth one is about naked singularity formation. So for Einstein vacuum equation, could a singularity other than black hole type form in gravitational class? So more precisely, can naked singularity emerge in vacuum spacetime? If we could have such a thing form, then the singular information could be sent out from the naked singularity. So together with my co-author Xuefeng Zhang, he's a postdoc in China, so we construct examples of naked singularity formation for Einstein vacuum equation in higher dimension, which is in 5+1, under spherical and self-similar symmetry with regular initial data prescribed here. For Einstein vacuum equation in higher dimension, we could form a naked singularity at this point. So the curvature blow up as a conic singularity here, and there's no trap surface to cover it, and the singular information could be sent out. And I want to say that the singularity formed here is a borderline case, which is much weaker than the singularity inside of black hole region. So for example, for this one, the Quasilinear scalar, which is a curvature square roughly, blow up rate looks like 1/r to the power 4. And for Schwarzschild case, the r at I equal to 0, Quasilinear scalar blow up looks like 1/r to the power 6. So in some sense, the singularity inside the black hole region is really strong. Not only we have a singular surface, it drags some region close to it to be black.
So
yeah,
all of this is for vacuum, is it?
This is for vacuum.
No matter. All of the
no matter.
theorems
No
you
matter.
mentioned.
Yeah, right.
And
Yeah.
you couldn't do it in 3+1.
We cannot.
3+1 with matter you can do.
Yeah, 3+1 with matter we can do.
Yeah.
But
Right.
vacuum no.
No,
With
no,
vacuum.
because we cannot put spherical symmetry. It's not hard.
I'm sorry, I have
Right.
a layman's question.
Right.
But where do the gravitational waves come from if there's nothing?
So the gravitational wave is about the first three results. I will talk about it later. So this is different. This is a naked singularity.
I see.
Right. So, okay, yeah. Okay, so we will answer these four questions by three different mathematical methods. one is hyperbolic approach, elliptic approach, and one dynamical system approach. So let's first talk about the hyperbolic part, which is, to be more precise, so in this talk, we use the existence of a trapped surface to indicate the existence of a black hole. It's a local object. So a two surface in our system is trapped if both its future expansions are negative. In 1965, Penrose have this famous singularity theorem. For our system, if our system contains a closed trapped surface, then the system would be future causally geodesically incomplete. So, but in 1995, Penrose didn't know whether trapped surface could form from data there's no trapped surface. So after this theorem, the singularity formation in GR is transferred to the formation of trapped surface in GR. And until 2008, Cristolo gave a positive answer. So let's see how to using gravitational wave to form a black hole or trapped surface. So this is the Penrose diagram we will use, and this is the future direction. So we will prescribe Minkowski data here, and we will put some large data here. Okay. So Cristolo introduced a small parameter delta. So this length is very small. So U equal to U infinity could be really large. When U infinity equal to infinity, it will pass down infinity. And we foliate our spacetime using U equal to constant and U bar equal to constant. This is U bar equal to 0, U bar equal to delta, U equal to U infinity, and U equal to C. C is roughly offset 1. And each point in this picture actually is a standard, it's a two sphere. For example, this is SC delta, which means U equal to C and U bar is equal to delta. E4 is outgoing direction, E3 is incoming direction. Given each 2 points, so we have the two sphere. We have E1 and E2 tangent to it, and then we can pick up the orthogonal frame. And based on two sphere, this is outgoing direction. We can define the non-second ordinal form, which is this one. So we further decompose into trace part and the traceless part. Traceless part also has the name of shared tensor. So we will prescribe Minkowski data here, put the large data here. But in the beginning, because it's very far away, the density is really small. But all these waves will travel inside. And when all this energy of waves goes to this region, the mass density is large enough. And then we can create a trapped surface here. That's the intuition. So what is the hard part? The hard part is, so although the physical intuition is really intuitive, but mathematically, we need to make sure that we have global existence, a long-time existence, which is Einstein vacuum equation. It's not hard to get a local existence, but Cristolo needs to make sure he has a global existence from really far away to U equal to 1. So this is a large data problem. For small data problem, roughly similar question, Cristolo and Kahneman already used 600 pages to prove global existence for small data.
That would collapse the black hole by itself.
Right, but this is sometimes a harder problem. Okay, sure. Let's say more precise. So, Cristolo proved the following result. So, formation of trapped surface. So, for Einstein vacuum equation with characteristic initial data, which is non-trivial shared tensor at a very far away. It's in such a shape, which is delta minus a half. This is really large over U infinity. And for the incoming cone, we prescribe trivial data Minkowski. Okay. So, and all these waves go to the center, and this would be a trapped surface. SC delta would be a trapped surface. So for this theorem, Cristolo needs both upper and lower bound for shared tensor. So, okay. So this is really large, but because one is very, very far away, so this quantity to be very small. So in L infinity sense, so this is to be very small. And in Cristolo's proof, a crucial thing is this form actually is roughly preserved. So at not only at U equal to U infinity, at any U equal to some constant, so the shared tensor would be on form delta minus a half over U. So this quantity is related to the Hawking mass density. So when this is really large, when U is very, very large, this is small. So that's why in the very beginning, we do not have a trapped surface. But at a later time, when U is of size 1, this quantity to be really large. So when U is equal to size 1, this quantity to be really large. And we could have a trapped surface. And the key is to show the global existence of Einstein vacuum equation in the large data region. Okay, so Einstein vacuum equation actually are a PDE system with 27 equations coupled by 13 tensorial quantities. So in Christolow's work, he controlled all the equations term by term, using 600 page. So after Christolow's work, now we have a more systematical way to control terms. So the new proof would be around 120 pages. Yeah.
You can't put it in a tweet.
So just something, so the hard part is to show that you don't get a singularity
Precisely.
before you get a.
Precisely. I mean, say we can solve the equation, can control the space-time before a drive surface is formed. Let's say if the PDE doesn't, we do not have well postulated, something bad may happen. We don't know what is the reason. Maybe singularity, maybe bad coordinate. Yeah. So we need to make sure everything is good in this colored region, and then we can talk about the physical intuition. Yeah. Okay. So the gravitational wave is coming from that direction. Okay.
What is the new thing that now you can simplify? What is
Right. So we have many geometric quantities. Now we can, based on the definition, give some signature and scale invariant norm. We can using different norm to prove things. And in some new norms, we can show that except the very few anomalous terms, the nonlinear term actually are low order. So that's why we not only track not track all the terms, we can only track very few terms. This makes the proof much easier. Still, lots right. Yeah. Okay. So after Christolow's work, we want to improve his result. And so with Jonathan, we introduced one more parameter, which is a large universal constant. So we still put Minkowski here, and along u equal to 1, we put shared tensor is square root of a, is a universal number, and let it go to the center. We get much smaller travel surface, which is roughly of size delta. A is 1,000 mega-1,000. Okay, so yeah, we still need the upper bound and the lower bound, and still in our case, shared tensor would be square root of a over u. So this result is sharp for delta respect to the method, which is we introduce one small parameter delta, we get a travel surface of size delta times a. So the benefit to have this parameter a, so if we let a equal to delta minus 1, actually we recover Christolow's bulk. And so in our proof, we only need a to be much larger than 1, less or equal to delta minus 1. So our initial mass input, if we check, which is delta times a, so for Christolow's case, if a is equal to delta minus 1, the initial mass input is of size 1. So that's why Christolow has a travel surface of size 1. So now our initial mass input is delta times a, so we would have a much smaller travel surface. This is indeed what we prove. And so to satisfy this condition, we could choose a is equal to log 1 over delta, or a is equal to log 1 over delta. The sharp case is a just a universal large constant, independent of delta. So for us, because our initial mass density is much smaller, we need to go further to get much smaller travel surface. So this is related to the scale critical thing. So if we check the size of initial data for Einstein vacuum equation, so we define the HS dot norm to be the L2 norm for the S derivative. Usually for nonlinear PDE, there is a critical norm associated to it. For Einstein vacuum equation in R3 plus 1, H3 half dot actually is a critical norm, which is with reaching scaling, this norm would be remain the same. So if we check this norm, so for my work with Jonathan, our initial data, which is H3 half dot is square root of a, H1 norm is very small. So for Christolow's data, if we pick up a equal to delta minus 1, H3 half norm is delta minus a half, H1 dot is of size 1. So our initial data is much smaller than Christolow's, and more importantly, this is a result for critical norm of like a constant. So in that sense, our result is scale critical, and it is the first scale critical result for Einstein vacuum in R3 plus 1. So there's some philosophy in PDE I talk about why HS dot norm is very important. So for study some simple semi-linear PDE, mathematicians learn some general philosophy for initial data. The largeness of critical norm may imply singularity formation. The smallness of critical norm implies no singularity. So this is a semi-linear equation, which is the box, the operator is independent of u. So this is a quasi-linear equation. It's more like Einstein. which is the operator here is dependent on the unknown. So quasilinear typically is much harder than semi-linear. Mathematicians got this philosophy from some semi-linear example. So Einstein's equation actually is a supercritical quadilinear hyperbolic system. Not only one equation, it's much harder than a semi-linear PDE. Philosophy A and B is still true. So in my work with Luke, we verify A, which is we construct initial data, which is H3 half dot norm outside square root of A, a large universal constant, and a trap surface could form in future. So singularity by Parent singularity theorem, something bad will happen in future. So this is the first critical result for Einstein vacuum without symmetry. For B part, actually it's still totally open at this moment. So Kleinman, Rogansky, Sheftel took around 10 years and 1,000 pages, many papers. They proved the celebrated bounded H2 theorem, which is for initial data. If H second derivative, the curvature actually is in L2 is bounded, then locally we have the existence. So the boundedness of H2 norm actually requires more than H3 half dot. We require more a half derivative, and so this big gap. So there is a bigger gap, and this is still totally open now. But at least with Jonathan, we verify the philosophy. A is right, B we don't know. This is from PDE point of view. Okay, so the additional difficulty to prove my result with Jonathan. So the trap surface we form compared with crystallus is much smaller. So we need to go very close to the singularity to get a very tiny trap surface. Instead of the decay rates, so all the geometric quantities in our work will have growth rate. So we employ the weighted estimate. So actually, before this work, actually I simplified crystallus result. So there I have some new way to do energy estimate. And using this weighted estimate to study decay rates, we can study growth rate. This is not enough. So when it's close to singularity, some curvature term actually behave really badly. They're out of control. So we employ the structure of Einstein's equation, 27 equation, and we do careful renormalizations to avoid bad term. This is very like what physicists did. So for example, when we control one curvature term, we call it rho. The evolution equation for rho actually is really bad. We cannot control it. But the evolution equation for rho minus some quantity actually is better. So now we can control the difference. And in another way, we can control this one. Okay, so that's like renormalization. And together with this, we can show the scale critical result. Okay, so after my work with Jonathan, so we have giving initial data can get a very tiny trap surface. So I realized, so this is the scale critical result. Usually given scale critical result, I can take a limit of it. And what's the meaning of it? So because so this is delta, and we have shared tensor, which is square root of A. Okay, so my work with Luke, we only need the largeness of A. We never use the smallness of delta. Thus, fix a delta, we have this right triangle. Giving a much thinner delta, we can go further. We can get resistance to this triangle. And if we let delta go to 0, actually I can, within the same initial data, actually I can get the existence of Einstein vacuum equation for the whole pink region. So this is very important. Not that we confine all the singularity in a very tiny ball. Along some direction, actually I can go to the center. Okay, this is after my work with Jonathan, we already noted this. But the question is, we want to make use of this region to do something. So this is the paper I wrote by myself, which is I constructing the boundary of the black hole region, the apparent horizon in this region. So the dashed line is corresponding to the apparent horizon, and this is the emerging boundary point. So, so the dashed line is the boundary of black hole region. That is a dynamical horizon, a space-like apparent horizon, and each point corresponding to marginal outer track surface. Okay, so I want to draw the picture here. So what's the meaning of this?
The apparent horizon become the event horizon
Later.
at 45 degrees.
Precisely.
Later.
But yeah, intuitively this would be according to the non direction. Right. So let's say fix a straight line is in incoming non-hypersurface, which is looks like a cone. We already knew it's quite inside, this is trapped. And which is outside, this is untrapped. So in more mathematical terms, trapped means the trace chi is negative. Untrapped means trace chi is positive. So chi is outgoing, the trace of the outgoing non-second form. The question is for free boundary problem. We want to find two surface such that the trace chi prime is equal to 0. Okay, so we want to solve it. This is the two surface. Let's omega is equal to theta 1 and theta 2, which is in S2. So because this is incoming cone, so the u bar coordinate is fixed. It is h bar u bar. So for each point, because it's a point in our 4-dimensional spacetime, it would have coordinate u bar, theta 1 and theta 2. I call it omega. Okay, this is 2 dimension. So okay, so let u is equal to 1 minus r omega. So this would be our unknown. And using for each point, let's assume with coordinate this, then we can, for this unknown two surface, we can rewrite this condition. This is equivalent to an elliptic equation for r, which is in blackboard, which is just this equation, which is Laplacian this quantity minus 1 over r, this quantity plus, minus 1 over r omega, and plus some number, plus some low order term is equal to 0. So, so here actually it is quasilinear because the metric here depends on the location, and the location according to r. So, what is this? This actually is the incoming mass energy. So along each angles, so we shoot some mass inside, and for each fixed omega, the mass actually I will shoot, which is f omega times u bar times a. So this is a reasonable assumption. This is a reasonable assumption. Yeah, I'll explain later. Okay, so for these equations, I can show that this equation admit a unique smooth solution for each incoming non-hypersurface. Okay, so not only so for each incoming non-hypersurface, now I can solve a multi-node trapped surface. Not only for one, actually I can solve a family of this equation. So for each different incoming cone, actually I have a unique modes. If you put all these modes together, because I can have a very good elliptic estimate, I can show you that this apparent horizon together is also smooth, and except at this point. And for open set of initial data, this apparent horizon is also space-like. So this so when I solve this equation, it's more like a geometric analysis problem. I need to get good upper estimate from C0 to C1 to C2 alpha, and I use the method of continuity twice to solve this equation. Okay, so this result actually is related to black hole thermodynamics. So I will explain. So assume the upper bound, which is like this, and require some lower bound for shared density square. The lower bound is reasonable because for each of this is square root of a. Together we have a, and this is u bar f omega, which is between some number close to 1. So this condition means roughly is close to homogeneous, which is along each directions we put roughly the same mass. So we have a unique modes. Okay. So for that initial data, I can show you that I have a smooth apparent horizon emerging from this point, and it is also space-like. So moreover, for define the area of each mode to be entropy, this is inspired by physicists. And the area actually is increasing toward the future, and the area goes to 0 from the center. So this research, which is the elliptic part, the construction of a apparent horizon, was inspired by Ashitaka and Krishna's work back to 2003. There, they give the definition of dynamical horizon, which is space-like apparent horizon. If they assume such a dynamical horizon exists, they can establish the black hole mechanics along the apparent horizon, the first law, the second law, the third law. The question is open is whether this dynamical horizon exist in our space-time, or can this dynamic horizon actually form in granular clouds? So they don't know. So my answer actually, this is my result is the first result. There's no symmetry assumption. I can show that dynamical horizon actually indeed exists, and it could form in granular clouds. And moreover, for open set of initial data, it could form from one point. So in another picture is so putting initial data here, we put some gravitational wave toward the center, and at a later time, there would be the first singularity, and a whole black hole region is emerging from that point, and the boundary corresponding to it, which is our planet horizon. Okay, so that's dynamical picture.
So as the area increases,
right,
the energy that falls in has also gone up.
Right.
Is it satisfying the
Yes.
law at every instant as it grows?
Right. This is somehow your intuition is right. So this let's say given each U bar, okay, this means the total energy incoming because it's increasing. So it is increasing. Yeah.
That's okay, monotonic, but is it actually proportional
Yeah.
at
So
every instant, or is it only finally true?
so if we cut off this input and the radius of the black hole would stay constant. So right. Yeah.
Oh.
Eventually approaching now.
I
Yeah.
see.
Yeah. That's the intuition. Yeah. Okay. Sure. So.
So the answer is only at the end state.
Yeah, I think it's really defined at the end state, but you can put your end state anywhere you want.
Right, but this actually we have the freedom, so not necessary to be this. We can change it. You can solve it. Yeah. So this result actually is okay. So for this result, because I can construct the apparent horizon, I check the second law. Actually, the second law holds, and which is this theorem. So indeed, entropy is increasing toward the future, and entropy goes to zero from the single point. Yeah. I think that's. I also borrowed a picture from black hole initiative. It's very beautiful. Thank you very much. Yeah.
This is looking back in the
Yeah, there's the fluid here.
yes.
Yeah, the jet. Yeah.
So are there any questions for the speaker?
Please. Yeah.
Yes, I didn't follow. So you
Yeah.
were solving this equation for R of W,
Right. Of omega.
And
Yeah.
you
Of omega.
impose this initial.
Right. This is reasonable initial condition. Yeah, which
Right.
is corresponding to here. So this is for the initial data. So for the initial data along here, in quantity zero data here, we put some this assumption here. Not only upper bound. Upper bound actually make sure that we have the existence for the whole colored region. I also need the lower bound. Tells us how much mass we put in, and this is the assumption for the lower bound, which is in such a form. This is reasonable because each of this is like square root of a. Square it, we have a, and the integration is from 0 to u bar. U bar is very small, so we have u bar. This is coefficient, which is close to 1, tells how inhomogeneous it is. Yeah. So roughly this is when it's close to homogeneous, I get a unique marginal trap surface. So interesting question is, can I make this region to be larger? And this is harder elliptic problem. I'm working on it, but yeah. Please, yeah.
So you said that in 4 plus 1
Yeah.
dimensions, you can make a naked singularity.
5 plus 1.
5
5
plus
plus 1. Yeah.
What about 3 plus 1? Do you
3
have any
plus 1,
theorems that you can prove?
We don't know actually. So for 3 plus 1, Einstein covered scalar field, Cristolo in 1994, constructing the naked singularity on the spherical and self-similar symmetry. But
So what about the vacuum problem?
it's harder. It's
It is
harder.
harder.
It's harder. So the reason is in one moment I can show you why it's harder. So for Cristolo's case, he using a dynamical system approach. Einstein's scalar field on the spherical symmetry and self-similar symmetry gives to you a two-dimensional ODE system. Starting from this initial data O, the goal actually to go to this line, which is corresponding to a naked singularity. Cristolo need to first bypass a singular point, change the coordinate, and find a trajectory goes to this singular point. And he divides the system region in many pieces to dynamical system thing. So our result actually generalize Cristolo's results in some way. But the PD approach would be really harder. So this is your ODE approach. But if we consider if we impose axial symmetry, so we will have a PD problem. So we would imagine something similar, like this. Starting from initial data, bypass some singular point, and by some region we need to go to one particular critical point. We do not have this machinery in PD yet, so it's hard. Yes. Yeah. Thanks. Yeah.
Okay, let's thank the speaker again.
Our next talk is a blackboard talk, so I guess we have to rotate.
Yeah, sorry for the inconvenience. Yeah, I guess I'll have to go.
Alright, so our second speaker is Lamprou. He got his PhD in Stanford University and is now in MIT in physics. He's a Pappalardo Fellow. And I guess today you will talk about geometry and
Geometry and
very
very yeah. So, thank you for the invitation. It's a pleasure to speak to such a diverse crowd. It does make my job more challenging, but also more fun. So my name is Lampros. I just started my postdoc at MIT, and my research is in high energy theory. So it is, I understand, a little bit different from most people's research field. So I expect this to be probably enlightening to the people who care about quantum gravity, and maybe a fun break from work for the rest of you. So my talk I'll try to give you a new way of connecting quantum mechanics and gravity. And in particular, I will try to relate two different concepts: the geometry of space and the phenomenon of Berry phases. And I will do so in the context of the holographic duality. I will explain what I mean by all these words, but skipping all introduction, let's start by remembering what Berry phases are. And I will do so in an example that you're all very familiar with, to set the stage. Consider a two-dimensional sphere and a vector on it. Now this vector is defined on the tangent space of this point, and our task is to move this vector around. In order to transport that vector to a different point, to the tangent space of a nearby point, I am free, in doing so, I am free to act with the symmetry of the tangent space. In this case, an SO2 transformation that rotates the vector about its axis. So in order for me to meaningfully define and consistently define what I mean by moving that vector from one point to the other, I need to define a map from that tangent space to the other one, a map that we often call the connection. So this defines for us a means of parallel transforming. And if the space on which we're moving has a metric, usually the way we define this parallel transport is by demanding that when we're moving along a geodesic, the angle of the vector and the geodesic remains constant. But now, since we have defined the means of transporting vectors on that sphere, we can play a game and we can start moving this vector about a loop. A simple loop that you've all seen many times before is the one consisting of these three geodesic segments. And using the usual rules, the rules that's mentioned for parallel transporting, you can see that by coming back to the original point, the vector will have precessed by some angle theta. This angle theta is related to the integral of the curvature over the region enclosed by the loop. This angle theta is an example of Berry phase. But this phenomenon of frame precession is a much more general phenomenon. This can be a physical space, let's say the Earth, with the velocity of a particle moving around the Earth, or it can be a parameter space of a quantum Hamiltonian. You can have some family of Hamiltonians defined by some parameters, lambda, and this vector, for example, can be the ground state, a vector in the Hilbert space of these Hamiltonians. In that case, the precession of the frame is the acquisition of a phase when we move in this parameter space around the loop. So, all this is familiar. What does this have to do with holography and geometry as I advertised at first? So now let's go back to the introduction I skipped earlier. Black holes have taught us that the universe is holographic. This comes from essentially the area scaling of the black hole entropy. Ordinary quantum mechanical systems, ordinary local systems, have an entropy that scales with the number of degrees of freedom, which in turn scale like the volume. But if the black hole entropy scales like the area of the horizon, this implies that a quantum gravitational theory has a vast reduction in the number of degrees of freedom relevant for the system. And this is assumed to apply to the entire universe itself, to the quantum gravity theory. Now, this would be a fantasy if we didn't have a concrete model in which these ideas can be articulated precisely. And this model for this talk will be ADS-CFT, the most well-developed model of this class. ADS-CFT is a type of duality between two completely different theories. One theory, the left-hand side, is the gravity theory, with gravity in a d-dimensional spacetime. In fact, it's a string theory, but at the low energy limit, it just reduces to ordinary general relativity with quantum fields propagating on that dynamical background. It's a gravity theory defined in space with a negative cosmological constant. At the low energy limit, let's focus on the three-dimensional case. In the vacuum of that theory is the so-called de Sitter space. It is for all practical purposes, you can think of it as a cylindrical box with time running upwards in this figure. This is the time slice. And this is a homogeneous space with a symmetry group SO 2,2. I'm restricting to the three-dimensional case so that I can draw pictures and can make things more clear. So we have a gravity theory with ordinary fields propagating in this. This defines the left-hand side of the duality. The right-hand side, the CFT side, is a quantum field theory. An ordinary quantum mechanical theory defining d-1 dimensional spacetime. And the difference is that this theory has no gravity. It's defined on just Minkowski space. So the gravitational dynamics of this theory is somehow encoded in the quantum mechanical description of the dual theory. This quantum field theory has an extra property, has a large symmetry group, which is a conformal group, which in 2 dimensions in this case is again the SO 2,2 group. And here's the one thing that you need to know about how this duality works in order to understand the rest of the talk. For every degree of freedom, at the low end description of this gravity theory, let's say a scalar field phi satisfying the Klein-Gordon equation with some mass, there is a corresponding avatar, a degree of freedom in the quantum mechanical theory, which I will call O delta. It's an operator with a specific conformal dimension. And the way we understand this correspondence of the degrees of freedom is by saying that at the limit, as we take the limit of the field approaching the asymptotic boundary of this de Sitter space, the field approximates with an appropriate rescaling. That operator is identified with that operator in the dual theory. It is in that sense that we often say that this d-1 dimensional theory actually lives on the boundary of this cylinder, because you identify the operators by the asymptotic limit of this. Right, so this gives us a first hint on how to relate degrees of freedom and how this duality works. The question I will ask in this context is the following. In the gravity theory, a meaningful thing I can do is to measure lengths of paths, or distances between 2 points. The question I want to ask is, what does this mean in the dual description, in the quantum mechanical theory? How can I measure the length of the path? So I will answer this in 2 steps, and the first step will be to refine this identification between the degrees of freedom on the 2 sides. This gives us a hint on how to map the degrees of freedom, but it works only at the asymptotic limit. We want to find a set of a correspondence that probes the degrees of freedom that live in the interior of this ADS space. But this gravity theory is diffeomorphism invariant, so whatever we have to do it in a diffeomorphism invariant way. So a special class of diffeomorphism invariant operators that, as will become clear later on, are natural in the context of the duality is the following. Let's take this to be a time slice of ADS, just for simplicity, and let's consider a spatial geodesic anchored at 2 points, x1 and x2. I can then construct the geodesic integrals of the fields phi over that geodesic. In fact, I want a a basis on the space of these operators. So I will construct a one-parameter family of these guys. K here is a real number, which is the integrals of the field with an appropriate basis of wave functions. Let me give these guys a name. I'll call them BK for the field phi. These are manifested diffeomorphism invariant. S is just the proper length on the geodesic. I'm using this to parameterize the curve gamma. Keep in mind that what we want to do is to first identify a connection between this description, these probes of the bulk theory, with the boundary division theory. But before we do so, let's first understand what these objects look like. As I said, the ADS space is a homogeneous space. It has a symmetry group SO2,2. When I select a geodesic, there's a subgroup of this isometry group that preserves that geodesic. This consists in that case of the boost that rotates that time slice about that geodesic. And another transformation is called the generator of this transformation H. And another transformation which fixes the time slice and translates along the geodesic. Let's call the generator of this transformation P. Now these operators BK that I defined for you over here, and it's on the commute with the boost operator. Therefore, they're invariant under these boosts, and they're eigenvectors of that momentum operator. Good. Now, notice that in defining this object, the geodetic integrals, I implicitly made an assumption. I chose a reference point on the geodesic with respect to which I'm measuring distances, with respect to which I'm parameterizing that S. I chose a point somewhere here that corresponds to my S equals 0. Now, of course, I'm free to choose that point anywhere I like on the geodesic. In fact, this transformation, the symmetry transformation that moves points along the geodesic, can shift the action, can shift my reference point. So if I define this operator which generates translations along the geodesic, then I can shift the reference frame, the reference point, simply by conjugating with that operator. But as you can notice from over here, changing the reference point, let's say from this point to this point, by some geodesic distance alpha, the normalization of this object will also change by e to the minus k alpha. So the action, I don't know if you can see it down here, the action of the symmetry transformation on that operator changes the normalization by phase, by e to the minus k alpha, alpha being the proper distance that I move the point on the geodesic. And I can do this locally for every geodesic. The reference points can be chosen arbitrarily on each and every geodesic separately. So let's illustrate, therefore, the phenomenon that I want to talk about. And the best way to do so is to introduce the space of geodesics. Let's construct a space where every geodesic maps to a point. Let's parameterize the geodesic, let's say, by the center point and the opening angle. So if I draw X and L over here, this geodesic will map to a point. The geodesic operators I define will define local objects over here. And I want to play the same game as before. We want to take this local object we defined and transport it on the space of geodesics to a nearby geodesic. Now, as with the case of the vector on the sphere, in transporting from one geodesic to the other, I have the freedom to act with the symmetry of my object. In this case, it's not the symmetry of the tangent space, it's the symmetry of boosting along this geodesic. So in order to meaningfully and consistently transport that object from that point to the next, I need to define a connection that will appropriately map the local frame of this geodesic to the local frame of that. So what's the proper way of doing this? Well, likely, the space of geodesics has a name. It's called kinematic space. And it's the subject of study of a field called integral geometry. And if you open a textbook in integral geometry, one of the first things you will learn is that the spatial geodesics of a hyperbolic plane, which is precisely what the slice of ADS is, has a geometry of two-dimensional de Sitter space. But this means that we have a metric on that space. And using that metric, we can therefore define a notion of a parallel transport. Mathematically speaking, we have a fiber bundle on that de Sitter space, and the connection that we're interested in is the connection of that bundle. But this
What corresponds to the phase, the change that there's a phase change induced in the transport, I assume.
Right, so the point is that we want to identify the connection which precisely maps the local frame of one to the other. I will discuss what the physical interpretation of the phase after we conclude this introduction. So, having the metric, we can now compute the connection, and now we can play the same game as before. We can start from a specific geodesic operator, bk, at some point, and move it around the loop in this space, and around the waist of the sitter, for example, and then come back to ourselves, and then by elementary arguments, this operator b will go to e to the minus k, and u to this p, k. And now you may ask exactly this question. What does this change, what does this Berry phase, this Berry precession mean? Well, the answer is actually that this Berry precession measures the length of a curve in the bulk ADS. When we're traversing that loop, what we're doing in the holographic context is that we're considering a family of geodesics that looks like this. Remember, this is x, the center point of the geodesic, this is the opening angle. That's precisely why that loop defines that family. So, the fact that this exponential, this integral of the curvature of the connection over that loop measures the length is another one of the results of integral geometry, but there's a nice geometric intuition why this is so. Let's take two geodesics. As I mentioned, the choice of normalization corresponds to the choice of placing a reference point on the geodesic. But these two geodesics have a common point. Therefore, it makes sense to choose a common point for the common reference frame. It's trivially then allows us to map the operators here to the operators there without any change in the normalization. But now let's consider a third geodesic. These two, let's call them 1, 2, and 3. These two now have a different common reference point. So in order to jump now from 2 to 3, we have to act with a U transformation that will shift that reference point from this place to this. But the action of that symmetry will introduce a normalization e to the k delta s, with delta s being the proper distance over here. But if we play that game, if we keep playing that game, then all I'm measuring is this sum of delta s's, and the acquired Berry phase will be this sum of all these delta s's individually. And as this family becomes dense, you can see that measuring the length of the curve, which is precisely tangent to this family. The claim at this point is that the set of geodesic operators have the phenomenon that when I parallel transport them in a specific way about a loop about this family of geodesics, they acquire a Berry phase. Let's now, in the next 5 minutes, let me explain to you why this is interesting. The reason why this is interesting comes from the fact, from connecting this to the quantum mechanical theory. I wrote the two equations that I wanted. So these were the two properties that these operators satisfy. And these are the two properties that we use in order to build their holographic avatars, their dual description in the quantum mechanical theory. Remember that the degree of freedom I'm using to define these integrals has a dual degree of freedom over delta. So the recipe is that find a an object in the CFT built out of this operator would satisfy these two operator equations. In this case, our job is not particularly hard because H and P are isometries of the original idea space, which are conformal transformations on the boundary. So by demanding these conformal transformations of the object, one can build it, and the general form of this object in the CFT is some integral of O delta with some free smearing function, and this integral is over the causal diamond constructed by these 2 points. Now, these operators are particularly interesting, however, in the conformal field theory. The first interesting property about them is that they appear in the OPE of operators for the experts. The second interesting property, which is the most interesting fact about them for the purposes of this talk, is that they are zero modes of the modular.
Sorry, what was F? Just some.
F is a smearing function, which we determine by demanding these two properties for our operators. H and P are two conformal transformations, the two generators of the conformal group. So this function can be fixed up to normalization by demanding that our operator transforms in a specific way.
And it's vanishing outside this diamond?
It is vanishing outside. You can represent this in either of this causal diamond or the complementary one. But since we are interested in associating an operator in a region to that geodesic operator, we can just safely choose that causal diamond as our equation. So these objects are zero modes of the modular Hamiltonian. Now let me explain what this word means. Remember now, in the dual description, this on the boundary we have a quantum mechanical theory. Each one of these regions, x1, x2, are described by a quantum state. In other words, by a density matrix. These density matrices are obtained by taking the global state and tracing out the degrees of freedom that live outside of this region. So the modular operator is another way of encoding the information of the state, and it's defined via this equation. I define the modular Hamiltonian to be this object. Now it turns out that when the conformal field theory is in its vacuum state, then the modular Hamiltonian for a region like this is precisely that operator H, which in the bulk boosts above that geodesic. So when I demanded this condition, essentially constructing the objects by this requirement, what I built was zero modes of this.
That's the modular Hamiltonian for the conformal field theory in that diamond there?
In that diamond, yes. It is the modular operator that describes essentially the state of living in that causal diamond. So when I demanded this property, I built the zero modes of this Hamiltonian. But now you can see why this also corresponds to a very phase in the quantum theory. Given a state, you can construct the density matrices for all these subregions. And you can construct the space of all modular Hamiltonians. So in playing this game and moving our region around, what we're constructing is a loop in the space of modular Hamiltonians. And now this example is essentially an operator version of the standard Berry discussion. We consider the path in the space of Hamiltonians, in our case the modular Hamiltonian. The zero modes are mapped into new zero modes, but with the acquisition of a Berry phase. And this Berry phase, when that theory has a holographic dual, in this context can be something to result.
It's a buried phase in the space of vacua of the modular Hamiltonian.
Yes, of the
Not
space
the
of
usual
zero
one.
modes of the modular.
Yeah.
One could construct, the restriction to zero modes is because we have a set of results from the past which allow us to make the connection to the bulk easily. But the existence of a Berry phase, of a parallel transport in the space of modular Hamiltonians, should be more general. It should be more general for, one could play this game for more general operators. But the place where we know how to play this game carefully is when talking about zero modes.
Can you remind me why the modular Hamiltonian has degenerate vacuum degeneracy?
Good. So there is a sense in which these operators, okay, I feel like I will have to say if one too many ingredients. Let's discuss, yeah, I will have to say a little bit too much about this. Good, so the point now is that so the claim, I'm sorry, is that this is a general thing that you can play in any quantum field theory, or in any CFT as a matter of fact. This Berry experiment in the space of modular Hamiltonians is a general quantum mechanical thing that one can explore. In that case, we are able to actually get results and connect it to the holographic. Let me make two comments and close. The first comment is that I illustrated this example in a very symmetric case in the vacuum, in pure and de Sitter space, where I have a lot of symmetry. However, none of the central ingredients of that story are expected to rely on that symmetry. Symmetry makes our calculations very simple in that case, but the phenomenon should be general. I don't know the precise mathematical formulas to generalize it yet, because this is very recent, less than a month old. But it will be very interesting to explore this from the geometric perspective and from the boundary perspective. Now, the final comment will be, does this have to do anything with black holes? I didn't mention black holes at all, although black holes are essentially the reason why we're even doing anything like that, in some philosophical sense. But so over here I will just leave you with a speculative comment. Each of these geodesics can be understood as the horizon of a Rindler wedge in ADS. So that's not quite a black hole, although it has the same structure as a hyperbolic black hole. But so we're building objects that live exactly on the bifurcation surface, and this action of this P generator, which was so central in the discussion of the Berry phases, is the horizon symmetries. So the question is, does this bear any resemblance to the story of soft hair that have been developed by people here? And if yes, if there is any sort of similarity, could this be the seed for a meaningful adaptation of that story in the ADS-CFT context, where we have a control of the gravity theory, of the UV description of the gravity theory? I'll leave you with that. Thank you.
You quickly mentioned this integral geometry result that says that if you know if you have H2, the Poincare plane, you immediately said, oh, okay, DS2 is the space of geodesics.
Yeah.
In general, that seems really hard to tell. So what is known about that? Is it known for higher dimensional ADS? Is it known, what if you break some of the symmetry of ADS? I'm thinking about NEC, for instance, which is kind of like ADS, but with less symmetry.
Good. So, all right, so let me make two comments towards answering that question. The first is that whenever you have a symmetric space, this is an easy game to play. You essentially, if you have a symmetric space, the symmetry is inherited by the space of geodesics, and then you ask which are the metrics on that space.
But by symmetric, you mean like it's a Lie group itself?
So in the case of higher dimensional ADS, for example, ADS are homogeneous spaces, and you can actually do that game very easily. Now you may ask, well, is this a story that's only... by the way, the story of integral geometry was not entirely crucial for that development. It just helps get to results really quickly. Now, in cases where you go away from the symmetry, there is the following... Here's one thing that I can tell you. Constructing the metric on that space is not entirely clear, but the geometric quantity that you're really interested in is a form, the so-called Crofton form. That Crofton form is precisely what you need in order to compute lengths of curves. That integral of the extensity of the connection over that loop that I was describing earlier can be recast to the integral of the form that I'm sorry, I'm losing my words. To the integral of the curvature, I'm sorry. And all you need is precisely that form. That form is the curvature form. It's called the Crofton form. And for example, in any two-dimensional geometry with an asymptotic boundary, you can construct this by taking the second derivative of the length of the geodesics with respect to the endpoints. In higher dimensions, you will just put some indices here. So while I can't tell you about the metric, and it is a good question whether this space admits a metric in a more general context, the crucial quantity is this form, which allows you to measure lengths. It's actually interesting how you measure lengths. The question that you invert the question to, instead of measuring length by integrating the tangent vector along the curve, you count how many geodesics intersect your curve. And this form gives you a density in the space of geodesics. So that's what you need.
And that's the length.
Any other question? Okay, I guess Lampros will be around today and tomorrow, and we have pizza at 4:30. Thank you.
Thank you.
Thank you.
Of course.